The previous videos have introduced the basic framework of SL, the negation, conjunction, and disjunction. This video introduces the rest of the machinery of sentential logic, the conditional and the biconditional. Imagine a situation at a fair where one of the vendors is offering pony rides. We might describe the situation in this way. If you pay, then you can ride the horse. How do we translate that sentence into SL? Well, as always, we'll need a symbolization key that specifies English language sentences, which we're translating to each sentence letter. Let P be you pay, let H be you can ride a horse. Now we'll translate this sentence as P arrow H, if P, then H. The symbol is called an arrow. It represents the logical conditional. We can read it as if, then. The if part is called the antecedent. Antecedent because it comes before the arrow. The then part is called the consequent. It's the consequence. It follows from the antecedent. Importantly, the conditional is an inferential relationship. If you know the antecedent is true, then you can conclude that the consequent is true. It doesn't say anything else about the relationship between the antecedent and consequent. Importantly, it doesn't say that the antecedent causes the consequent. The arrow isn't a makes it happen. It's a allows you to infer. To see that explicitly, consider this example. In the same situation as before, if you can't ride the horse, then you must not have paid. Using the same symbolization key, we can translate this as not H, arrow, not P. Obviously, not being able to ride the horse is not what made you not pay. It's quite the opposite. Your not paying made you not be allowed to ride the horse. But the sentence tells us that were we to learn that you couldn't ride the horse, we could conclude that you hadn't paid. If you aren't allowed to ride, then it must be that you haven't paid. That's what the sentence says. And we symbolize that with the arrow. Now consider this sentence. You can ride the horse only if you pay. Our first sentence said that if you paid, then you could ride the horse. And it leaves open the possibility that there are other things besides paying that would allow you to be able to ride the horse. Maybe there's a random door prize. Maybe the vendor is an old friend of yours. Maybe you can sneak onto the horse while the vendor isn't looking. In contrast, the new sentence says that the only way you can ride the horse is to pay. There's no other way you could end up being able to ride. So for that reason, we can translate this sentence as H arrow P. Because the only way you could ride is if you had paid, then if you can ride the horse, we can infer that you must have paid. So A arrow B can be used to translate sentences of the form if A, then B, or A only if B. Just like with the other connectives, we want to fill out the truth table for the conditional, because all of the connectives in SL are going to be truth functional. That is, the truth of the compound sentence using that connective only depends on the truth of the two parts. However, there's something kind of problematic here. The English sentence if P then H doesn't really depend on the truth value of P at all. If P happens to be false, what we want to know is what would happen if P were true. Like, what would happen to H if P were true? However, because we're going to make P arrow H truth functional, we can't capture that subtlety, what would happen if things were different. So think about the sentence again. If you pay, then you can ride the horse. It allows for two possible situations. One in which you can ride the horse, and another in which you haven't paid. So let's paraphrase the sentence in this way. Either you can ride the horse, or you haven't paid. That we can translate into SL this way: H or not P. Since we already have the truth conditions for negation and disjunction, we can work out the different possibilities. We have 4 rows because there are 4 possible combinations of truth values for P and H. Not P just toggles the value, where P is true, not P is false. Where P is false, not P is true. And then H or not P, we just look at the columns for H and for not P and apply the rule for disjunction. And we get this table. H or not P is false only in this case, where H and not P are both false. That is, the case where P is true and H is false. So we'll use this same truth table, these same truth conditions for P arrow H. And that gives us this truth table. This is called the material conditional because the truth value of the compound P arrow H is determined by the actual truth values of the parts. That is, by the separate truth values for P and for H. Now, for formal reasons, we're requiring that the connectives of SL be truth functional. And this is really the best we can do with the conditional. But as we saw in English, conditionals aren't always material conditionals. Often they're subjunctive, saying not how things are, but how they would be, even if things were different. And often in English, we require relevance. The antecedent and the consequent don't just have to have the right truth values, they have to have something to do with each other. Trying to build all that into SL would be a lot more complicated. However, counterfactual logics and relevant logics that add this kind of extra machinery, allowing for subjunctives and for relevance conditionals, typically build on a foundation of a simple formal language like SL. So in SL, our conditional will be a material conditional. That means it's truth functional, it has this truth table, and there's a decent amount of work we can do with this, acknowledging at the same time that it leaves out a lot of subtlety of the English language if-then construction. So even though it's not perfect, our conditional in SL has this truth table. It's false only in the case where the antecedent is true and the consequent is false. It's true in all of the other cases. Now consider this sentence. This is a triangle if and only if it is a 3-sided plane figure. As always, we need a symbolization key. So let R mean this is a triangle, and let P be this is a 3-sided plane figure. We know how to translate if-then sentences and only if sentences. We learned about those earlier in this video. So we could translate the sentence using just symbols we already have. We could paraphrase the sentence in this way. If this is a 3-sided plane figure, then it's a triangle. And it's a triangle only if it's a 3-sided plane figure. And we can translate that as P arrow R and R arrow P. However, if and only if is a common expression in mathematics, so it's traditional to add an additional symbol. So to say this is a triangle if and only if it's a 3-sided plane figure, we use the double-headed arrow and say R if and only if P. The symbol is called a double-headed arrow. And it's like the regular arrow, but it works in both directions. It represents a logical biconditional, which is like a conditional, but it's bidirectional. We can read it as if and only if. The truth table for the biconditional is like this. It's true if and only if the two sides have the same truth value. So if R and P are both true, R double-headed arrow P is true. If they're both false, our double-headed arrow P is true. Now, if the two sides have different truth values, then it comes out false. Importantly, this doesn't mean the two sides are logically equivalent. It just means they at least happen to be equivalent. That as a matter of fact, they do have the same truth value. In this video, we've introduced the conditional and the biconditional. We've learned the truth functions for each of them. Now this gives us all the symbols of SL. You should get comfortable with the truth conditions for the connectives. If you have them memorized, you'll have an easier time with truth tables next week.